Hi, this is part 3 of chapter 3. Okay, this is part 3. Okay, so for this video, you will only learn how to set up stoichiometric table for a flow system. For this learning outcome number 2, we will cover in part 4 of the lecture. Okay, so we have done for a batch system. Okay, so for flow system, we also look into the constant volume. Okay, so taking A as the basis, so divide all the stoichiometric coefficient with the stoichiometric coefficient of A. Okay, the form of stoichiometric table for flow system is basically similar to batch system. The only difference that we replace the N, J is any species not with F, J is represent any species not, and N, J we replace with Fj. Okay, so this is the stoichiometric table of a flow system. Okay, we have all the species and also the symbol. Okay, so you just replace the N with the F. And the rest will be the same. Okay, some definition on the parameter that we use in the table. So theta I is equals to the Fi naught of any, this one will be any species, Fb naught or Fc naught or Fd naught over divided by Fa naught. It is always divided by the basis of the calculation. Ca naught, Ci naught over Ca naught or Yi naught over Ya naught. So theta is the change in the number of moles. So we have product minus the reactant, and we also have Ci equals to Fi, because this is a flow system, Fi over V. Okay, some note for you to remember. For a liquid phase system, there is no phase change, so the volume is constant. So we have V equals to V naught, and we have Ca equals to Ca naught times 1 minus X. However, this equation cannot be used for a gas phase system, because for gas phase, we need to include the volume expansion into the calculation. Okay, now we look into a system where volume change with the reaction. So it occurs when a system does not have an equal number of product and reactant. So it usually involve gas phase system. So for example, we have an N2 plus 3H2 producing 2 mole of ammonia gas, and also in combustion reaction. So we need to take into account the expansion factor, symbolized by epsilon, which is equals to the change in total number of moles for complete conversion divided by the total number of moles fed to the reactor. So at complete conversion, X will be equals to 1. So we have epsilon, the expansion factor will be epsilon equals to change in the number of mole. This is delta times the Na naught divided by Nt naught, which is equals to Ya naught times the delta. So this is the coefficient, the number of mole of product minus number of mole of reactant. Okay, so this is the volume expression for both batch and flow system when we include the expansion factor. So this is the main assumption. We have P constant and the T constant. It is isothermal reactor system. So P0 over P1 is equals to 1 because it is constant. Initial and final pressure is constant. Initial temperature and final temperature also constant. So it is 1. So you will have the final equation for batch is this. And for flow also, P0 over P equals to 1 and T over T0 equals to 1. So your final equation for a flow system will be equals to this one. But how do we get this equation actually? So you can try to derive those equations. So the trick is by using the ideal gas law. You can refer to page 111 to 115 to make you understand better how to derive this equation. Okay, this is the end of part 3 of the chapter 3. So in part 4, you will learn how we will do one example and you will see how to apply the expansion factor.